Welcome back, folks. This is section 7-2, which is part of chapter 7. Chapter 7 being interval estimates, and this is recording number 1. In section 7-1, we were talking about confidence intervals for the mean, and in this situation we assume that we know what sigma is, sigma being the standard deviation for the population. And there could be any number of reasons we think that we think that we know what the standard deviation of the population is. In the new section 7-2, we're talking about basically the same thing, the confidence intervals for the mean. However, in this section, we do not assume that we know what sigma is. So we say that sigma is unknown. So we're going to have to approach this in a slightly different manner. Before we start that, though, this page right here is at the end of chapter 7. This is the summary page of the textbook. This is the PDF version. If you take my advice, what you'll do right now is stop this recording, stop watching this video, and go to that summary and read this over again. It's going to make a lot more sense this time around if you do it this way. Obviously, it's not a good use of my time or the video time for me to read this to you, but you've got to do this because this is a very difficult chapter, and I want you to understand that it's going to take you several iterations. It's going to take you several times before you understand this chapter. Now this is the next page. This is important formulas. This is the formula that we have been talking about. There's a lot that can be learned just by looking at a formula. So for example, this is the formula for the confidence interval of the mean when sigma is known. Okay? So what we're saying is that mu is in this interval, x bar plus or minus this margin of error here. I want you to notice that the n is in this bottom of this term. As n gets large, the square root of n gets large. And when you have a larger and larger number in the denominator, the fraction itself gets smaller and smaller, right? For example, 2/3 compared to 2/5. Well, who's bigger? The 2/3 is bigger. 2/5 is smaller. How about 2/100? That's even smaller yet. So as the denominator gets small, the entire fraction itself gets smaller and smaller. So what is this telling us? As n gets large, as the size of the sample gets larger and larger, this term gets smaller and smaller. Therefore, the entire term here, I said term, but I should say a factor, I guess, because we're multiplying. So this factor right here that's called the margin of error. That gets smaller and smaller. So as n gets large, the margin of error gets smaller. Well, that's exactly what you would expect. When you have a larger sample size, you're going to have a smaller interval that estimates the mean, the interval estimate of the mean. And that's what you would expect. A larger sample size is certainly better than a smaller sample size. So there's a lot to be learned just by looking at these formulas. Now in the next, that's section 7.1. In the next section here, it's not marked, but this is going to be the formula we're going to use in the next section. 7-2. And I believe if you just compare on one piece of paper, compare this with this, you'll agree with me that they're very similar. The only distinction is this right here, this appropriately chosen z value in section 7.1 is compared to the appropriately chosen t value that's in section 7-2. In addition, in 7-2, we don't use sigma, we use S. That's the sample standard deviation. whereas up here we use the population standard deviation. So it's very helpful. I strongly urge you to make a copy of all these formula pages. It's very handy to be able to look at one page and to see the appropriate formulas for the entire chapter. Okay, so back to the book here. Section 1 is when sigma is known. I'm sorry, I may have said that wrong. Section 7-1. 7-1 is where sigma is known. 7-2 is where sigma is not known. But in both of these, we're looking for a confidence interval for the mean. And again, we are estimating the interval of where we think the mean of the population is going to lie. It's going to be somewhere in this interval, and we're going to have a certain level of confidence. So 7-1 was kind of the gist, G-I-S-T, the gist of something. Is kind of the main part of something, the most important part of something. So 7-1 was kind of the gist of the techniques. Everything else from now on in chapter 7 is going to be just different ways of calculating the same basic idea as we had in 7-1. So I hope you spent the time necessary on 7-1. Okay, so here we are in 7. Oops, give me a second here. Okay, so here we are. This is 7-2. We're going to learn how to we're going to learn how to calculate confidence intervals. And again, it's for the mean, but this time we don't know what sigma is. Okay, and that's what he talks about right here. Okay. Now he mentions this one more time in passing, but it is important to realize that if the sample size is 30 or more, we don't care if the population is normally distributed. We care, but it doesn't matter. This formula still works. On the other hand, if the sample size is less than 30, then a requirement is that the population has to be normally distributed. Okay, and as he says here, the author says most of the time the value of sigma is not known, so therefore what we have to do is we have to do our best guess. So we have to essentially estimate what sigma is. I don't like that word estimate because we're using estimate in a different way here. We're not estimating what sigma is. What we're doing is we're saying, hey, listen, I don't know what sigma is. The best I can do is use S. S is the standard deviation for the sample. So I'm not really estimating what sigma is. I'm just putting in my approximation to make the calculations work. Okay. All right, so I'll let you read that yourself. And what he's giving you here is he's telling you, okay, listen, we're not going to use the Z distribution. We're now going to use the T distribution, also known as the student T distribution. The word student actually, I believe, is named after the mathematician that kind of came up with this. His name, strangely enough, was student. Okay, so they have to be simple random variables. Okay, in other words, when we say simple random variable, what do we mean by that? And I apologize, I may have said that wrong. I may have said simple random variables, but that's not what the book says. He says simple random samples. Okay, so what does he mean by simple? Simple is as distinguished from compound. So I'm going to let you look at your book yourself. But on page 189, he talked about what's the difference between a simple event and a compound event. An event with one outcome is called a simple event. So for example, the event of getting an odd number when a die is rolled is called a compound event, since it consists of 3 outcomes or 3 simple events. Now, does that make sense? In other words, if you toss a die, if you want to get a 6, that's a simple event because there's only one way of getting a 6. That's a simple event. That's one possible outcome that will give you that simple event. On the other hand, if you're talking about rolling an odd number, well, that's a compound event because there's different ways that you can get the compound event. It's 3 possible outcomes will give you an odd number, 1, 3, and 5. So that's on page 189 at the top of your page. So when you see a word like this, when you see something like, like right here where it says I'm sorry, I lost it. Simple random samples. don't just read it and keep on going. You got to make sure you understand what that word means. So do what I just did, and that is I looked it up in the index. I went to that page to refresh my memory. Every word counts in a math book. Back to the book here. The concept is very similar, very similar to what we've already done, except we have a different formula, of course. And the key distinction is that we use the t distribution for our coefficients rather than the z variables, or the z values for our distribution. Gosh, I didn't say that right again. Let me say it one more time. In section 7.2, when we're dealing with confidence intervals when sigma is unknown, we use the t distribution. In 7.1, when we think we do know what this standard deviation of the population is, we think we do know what sigma is, we use the z distribution. So that here's 1 second. This is talking about what the t distribution is. It's similar in some respects, and it's different in some respects from the z distribution. Now that's a trivially true statement, right? If it was exactly the same, it would just be another name for the z distribution. So it's bell shape, it's symmetric, and so forth. So let me let you read that. I would say the most important concept is that the t distribution is a family of curves. It's a whole family of curves, and the family is based on the degrees of freedom. Now, we have not defined that term yet. We'll see that in just a moment. But it's a t distribution is based on the degrees of freedom, and that's related to the sample size. But what I want to tell you is that as the sample size gets bigger and bigger, the t distribution starts to look more and more like the standard normal distribution. So here, the black curve here is a standard normal distribution. This dashed blue line is the t distribution. And depending upon the degree of freedom, as you can see, it starts to get closer and closer to the z distribution. Okay, so I want to explain what degrees of freedom is, but let's save that for the next tape.